hear it. I hope it's not be the last whiteboard talk, but you'll have to play a role in it. So, of course, please feel free to interrupt me at any moment. So we're going to talk about sharp thresholds, and sharp threshold is something that you must have all seen in the news recently, but we're not talking about this type of threshold. So what we'll have is we'll have a Boolean function on the discrete cube, and we're always going to have the function to be monotonic. And by that we mean that x and y such that xi is at most y on each coordinate, then f of x is at most f of y. Okay. And we'd like to put a measure on the cube, so we'll use the p-bias measure. Which is mu p to the n. So mu p is the basic measure on bits, which is 1 with probability p and 0 otherwise. And then we take a product measure, and this is what we have on the. So what is the most basic thing you can ask about a function in this measure? Well, you can ask, what is the average of the function according to this measure? Okay. And then you can study this mapping. You can study the mapping from P to the average of F according to mu P. And what we want to do is we want to understand the behavior of this map. So here are two distinct behaviors. So on the left, we have what is called a coarse threshold. On the right, we have what is called a sharp threshold. And what this words refer to is this interval in which the function becomes from almost having average 0, almost having average 1, whether it is very narrow or very wide. So if it is very narrow, we say that the function has a sharp threshold, and if it's coarse, if it's wide, we say it has a coarse threshold. Okay. And yeah, so we want to understand when does a function have a sharp threshold and when does it have a coarse threshold. So, okay. So if I tell you the answer in one sentence, the basic intuition is if you want your function to have a coarse threshold, it must be for a reason. So a function has a coarse threshold if and only if it has a local structure. Okay, so this is of course not formal. It doesn't really mean anything, it's just the intuition. And in some cases we know how to prove it, in other cases we don't know how to prove it, but maybe some partial results. And really the theory is divided into two regimes. There is the first case where your P is bounded away from 0 and 1. This is kind of more well understood. There is a second case, which is more challenging, that P is either close to 1 or 0. Let's say it's close to 0. So when P is little of 1, let's say P is equal to 1 over root n. Okay, so these are two regimes, and we know much more about the first one than the latter one. Okay, so this is what sharp thresholds are. So what are we going to do with them today? So here is the plan for today. So first of all, I'm going to tell you about the most classical sharp threshold result by Friedgut, which we've actually already seen 2 weeks ago. Then I'm going to show you, as the title suggests, how to use such results to solve problems in extremal combinatorics. So more precisely, we're going to study the structure of intersecting families. So this is a result of Dinur and Friedgut. Yeah, so actually when I was preparing the talk, I was more ambitious with the plan that I had in mind. So we'll actually spend a fair bit of time showing this result. Then finally, I'm going to tell you about some new sharp threshold results. And as much as time allows me, I'll show you new application to extremal combinatorics. Okay, does the plan make sense? Okay, good. So let's start discussing this classical sharp threshold result. So let's go back to the previous slide or whatever. So how do we distinguish between these two? The most obvious thing to do is to look at the rate of increase, which is just the derivative. So we want to look at the derivative of the average of f according to p with respect to p. Okay, and when this derivative is large, we're going to have a sharp threshold. When it is small, we're going to have a coarse threshold. Okay, so sort of our goal is to say something like, if this derivative is small, then the function must have the following type of structure. Okay, so this is the following result of Friedgut. It says that for every k and for every epsilon greater than 0, there is some delta such that if I give you a Morton function, so I also need a j. So if I give you a Morton function, and I tell you that it has a coarse threshold, then it must be for a reason. Second. Then f essentially depends on at most j coordinates. Okay, so for now, forget about these two parameters. They're not important. What this result is saying is that if you have a coarse threshold, then this is because you depend on very few coordinates.
So the derivative is bounded everywhere, right?
So on a specific point. So
no, it's not any specific point.
Yeah. So okay. So I haven't said that.
Parameter is p. It's not the point x.
Yeah, there is no point x. So sorry, I should have made it clear. Okay. So before we go into all of this discussion, we're going to fix our favorite p. Let's say p is equal to half. So we're going to focus on the first case for now. Okay. So let's say that our p is half or quarter or anything bounded from 0 and 1. Okay. And what I'm telling you is that the derivative at a specific point at this p is bounded. Okay. And now I want you to prove the structure for me on this very specific p.
Yeah, it's a bit confusing, the notation, but it's okay. I mean, I think you understand. Maybe you should call it P naught or something.
Okay, good. Yeah. So yeah. So we have this P naught, which is the P that we care about. Let's say half. Then if your derivative is small, then you essentially depend on at most j coordinates. So this is the informal version. The formal version says that, well, there exists a function that depends on at most j coordinate. That is close to f under this specific distribution. Okay, so this is sort of the more formal meaning here. I wanted to say it because this distribution comes into play when you measure distance. And morally, at least, this is an if and only if statement, because if you have a function that depends on at most j coordinates, then you can show that the derivative is at most j on each point. But of course, formally, you only have closeness, so it's not an if and only if statement.
No, I think just to clarify, first of all, g is a function that depends on at most j coordinates, might as well be a monotone function. And as such, it just means that all its min terms are just sets of at most j variables. So it's an OR of ends where every end is on j variables.
Yes, exactly. So yeah, so as Avi said, you can assume that G is DNF with J, even monotone. Right, Avi? Good. So this is a theorem, and if you remember the KKL theorem from last week, or from 2 weeks ago, this is really a related result, and you prove it really by a similar way. And actually, I think that we mentioned it that time. Yeah, so it's a very nice result. But you'll probably agree with me that it doesn't seem like it has anything to do with extremal combinatorics, with the study of how large can a specific object be if it satisfies some properties? Good. So this is a let's put that all aside for now, and let's talk about extremal combinatorics. And so definition. So in this talk, we're going to change from the language of functions and families of subsets very often. And I want you to sort of identify a subset of n with the indicator vector. But we'll move from this language very often. So let calligraphic F be a family of sets. We say F is intersecting if any two elements in it have non-empty intersection. Okay. And the question. So let's fix a P. And let F be intersecting. How large can it be? Okay. So let me just clarify for one moment. So previously we defined the mu p measure to be on vectors, but as I told you, you can move from vectors and subsets interchangeably. So this is also a measure on sets. And the question is how large of a mass can an intersecting family have? Well, so let's first say that this question is not really interesting for parameters p, which are more than half. So I claim that for p that is more than a half, say is 0.51, this question is not really interesting because they are very, very large intersecting families. Does anybody see what they are? Okay, so these are the majority sets. So we take all subsets of n whose size is more than half n. Okay, so you can easily show that this family is intersecting, but if you take like a bias parameter 0.51, then the measure of f is almost 1 by some Chernoff bound. Okay, so the question really only makes sense for a p that is smaller than half. And for us, the discussion today will be focused on p that is bounded away from half. So today, good. Yeah, so by the way, this question, as you might have seen earlier, this is called Erdős-Corrado, or this type of question is called Erdős-Corrado style results. And this specific one is not too hard, but we're going to build up to something more interesting. Yeah, so here is an easy claim. So suppose f is intersecting, then I claim that if you look at the mu half measure of f, then this is at most half. Okay. So let's see the quick proof. So I claim that for any subset A, either the subset or its complement are not in F. Or writing it differently, the sum of indicator that A is inside F and that A complement is inside F is always at most 1. And why is that? Well, it's because these two sets have empty intersection, so they cannot both be in F. So if we take expectation now over uniform A, we get a result. Okay, so we sort of solved the problem without any difficulty, and this is tight. For example, we have the dictatorship function. Good. So the p equals half case is solved. Now I'm not going to show you that, but you'll have to trust me that you can prove it in numerous ways that this result does not only hold for p equals half, but also for any p less than half. So for any p less than half, if f is intersecting, then the mu p measure of f is at most p. Good.
Dora, just a quick question.
Yeah.
So didn't you show last time that the total influence of a function is at least 1, and you can deduce it immediately?
Yes. So in this talk, I wanted to refrain from saying the words total influence, but you are right. So in this, yeah. So good comment. So if you see in the first slide, today we chose to talk about these derivatives, and we 2 weeks ago we saw that it has relation to the total influence, and actually once we see that, it's not hard to deduce the second claim from the first claim, as Andre suggested, and this is did one of the proofs. The other proof is by some sort of Hoffman bound, but yeah, I don't want to get into that. But yeah, thank you, Andre.
Yeah, just a comment. If you want to see 4.5 proofs of this theorem, Friedgut gave a beautiful talk maybe 2 years ago. You can look at the video site of our lectures, CSDM lectures, and enjoy yourself.
Yeah. Yeah. Good. Good. So we solved the question, but this is not really the question that Dinu and Friedgut try to solve. They try to understand the stability question. So here's the question. So suppose we have an intersecting family. What can you tell me about its structure? Okay. Of course, if this family is very small, this question doesn't make any sense because you cannot say much. But there are two regimes of interest. The first one is when your family has size which is very close to the optimal. And in this case, typically what you want to show is that f is close to an extremal example, which in this case turn out to be only dictatorships. Question. So this is not a question that we will care about today. We'll care about the second question. So now I allow you for the intersecting family to be much smaller. I only assume that it has non-negligible size. And I ask you for its structure. Yeah, so of course here you cannot hope to say that it's close to a dictatorship or anything along these lines, but you can still hope to say something interesting. Okay.
Though maybe just worthwhile to say that stability questions are all over the place in analysis and in geometry and in combinatorics. It's the general question: if you have any inequality that applies to all whatever, all functions, all I don't know, hypergraphs, all sets, all whatever, then the interesting thing is what happens. What structure do you have if the inequality is nearly tight? So it's just a very, very special situation which is studied in amazing generality all over the place.
Yeah, so that's a very, very good comment. So actually, I originally come from PCPs. This type of questions arise all the time. You want to prove that if a function has certain properties, then there are some distinct variables because it's related to analyzing PCPs. So this specific question, I'm not sure if it is motivated by these type of questions, but there are certainly a lot of them. Yeah, so let's.
I should say that it's motivated from, usually it's motivated even before applications. It has many applications in many domains, but it's sort of a gut reaction of any analyst who proves any inequality or geometer. What does it look like if the inequality is nearly tight? What are the objects that satisfy the inequality for which the inequality is nearly tight in whatever regime? So it's even before applications, one of the most basic questions about inequalities, which are all over mathematics.
Mm-hmm. Yeah. Good. So let's show a few examples. So the first example is dictatorship, of course, meaning the family of sets that contain element 1, but actually also any subfamily. So if you take any subfamily of dictatorship of large measure, then it's still a valid example for the second question. So more generally, you can sort of design a family which is obviously intersecting, and then take any subfamily of that. So for example, you can take the family of all sets that contain at least two of the elements 1, 2, 3. And again, any subfamily. Okay, and I can go on with these examples, but I hope that you see some pattern. The pattern is that there is some family which is obviously intersecting, because this is the way we defined it, and then we can take any subfamily of that. And in a sense, Friedgut showed that this is the only type of examples that exist. So this is what says the following. I'll state it informally first. So suppose F is intersecting, and it has significant measure, then there is a junta family G, meaning a family that only depends on a few of the elements, such that, first of all, G is intersecting. Secondly, the family F is almost contained in G. So I'll write it a bit relaxed like that. By that I mean that if you look at the LOM elements of F that are not inside G, then these are smaller. Okay, so I hope that you see how this theorem aligns with the previous example. We have some obvious families, like this family. I guess I should I should have called it G. It makes more sense. We have these families, which are juntas. They depend only on few variables. This one depends only on one variable, and this one depends on 3 variables, such that they are clearly intersecting. And then we can take any subfamily of that. And you can, of course, insert some junk, but it only be very little. Okay.
So the size of the junta depends on delta for P fixed.
Yeah, so this is a little bit informal, but there are 2 parameters here, the epsilon and the delta. The size of the junta will depend on both of them. Okay. Okay, good. So the majority of our effort today will be to prove this theorem. So maybe I'll not give you a full proof, but I'll give you like probably most of it. Because I think that it's really cool and it uses some very neat ideas. Yeah, so how does this relate to sharp thresholds? So we'll soon see it, but let me first give you an overview of what we're going to see. So first of all, we are going to define some notion of pseudo-randomness. which I hope then you'll see why sharp thresholds will enter the picture at all. So then we're going to state a regularity lemma. So we've seen several talks about regularity lemmas already. And these lemmas roughly say that once you have some notion of pseudo-randomness, then you can take any family and partition it into pseudo-random parts plus some junk. This is exactly what we'll do. Then, roughly speaking, you will show that pseudo-random families cannot be intersecting. And from these three ingredients, we'll show the proof. So these are the three ingredients of the proof. Good. So any questions so far? Yeah. So now I'm going to define for you the notion of pseudo-randomness that we'll use in this talk. But first I have to define restrictions. Yeah. So let's say we have a family F. We have some subset of coordinates I, and we have some further subset of it A. So the restricted family F when I is restricted to A is the family of all sets, subsets of n minus I, such that if you add to them A, they're inside your family. Okay, so
you prefer restrictions on Boolean functions. This is just where you set the variables in I to 0 or 1, depending on whether they are in A or not, and leave all the other variables free.
Exactly. So before we say an example, let us say what are we saying. So if indeed we prefer to talk about Boolean functions, so we look at the corresponding Boolean function to the family, then this restriction amounts to saying we fix variables of I to be 1 inside the coordinates of A and 0 otherwise, and the rest we leave free. So this is really the same as this. And so let's see a quick example. So let's take our dictatorship function. So for that, if, for example, we look at the first variable and restrict it to be inside, then we get everything. But if we fix it to not be inside, then we get nothing. Okay, so this is the notion of restrictions that we are going to use. This is a very basic notion that is very useful. Yes, I need a bit more space, so I'll have to erase that. And here's another definition. This is the pseudo-randomness definition. Yeah. So we say F is R epsilon pseudo-random if, so let me say before, so now you can look at any subset of at most R coordinates and fix them in whatever way you want. Then we say that a function is, the family is pseudo-random if, however you do that, does not change the measure of the family too much. So if for every subset of size at most R, and any setting to it, if you look at the measure of your family after you restrict it, and the measure when you don't do anything, then these are very close. Okay. So I want to spend a little bit of time talking about this pseudo-randomness notion. So if you've seen all of this Fourier analysis business, then this is roughly equivalent to all small Fourier coefficients being not significant in magnitude, because this really corresponds to Fourier coefficients of R and its subsets. So that's one thing. The second thing is that maybe this.
Say it again. We are looking at Fourier in the p-bias measure.
Yeah. So if you look at this function, the indicator of the family, then the pseudo-randomness notion is roughly equivalent to all Fourier coefficients of F of subsets of R to be smaller. Okay. Sorry. So it's roughly equivalent to that. And the reason I say roughly is that you lose some parameters, but other than that, it's really equivalent. So the second thing that
subsets of R, this is for all R. This is, so you're saying all small Fourier coefficients.
Yeah.
Are small.
Yeah, non-empty to be precise. Yeah. Good. So this is one thing. The second thing is that maybe at this point, it should already be somewhat hinting that sharp thresholds will enter the picture, at least in some way. So why is that? So let's go back. Yeah, so let's go back to Friedgut's theorem. So these are a lot of words, but what I'm trying to say here is that Friedgut's theorem tells you that if you don't have a sharp threshold, then you depend on a few coordinates. And in particular, you can take these coordinates, fix them to your favorite value, and get that your function is either very close to 0 or very close to 1. But the important feature is that it really changes the function. So this is really in sharp contrast with pseudo-randomness. So what I'm trying to say is morally, but you need to prove it, it's true. So Friedgut's theorem will allow you to say that once you have pseudo-randomness, you get for free sharp threshold. And again, let me repeat the reasoning. So Friedgut tells you, so maybe let's say it. Here's the reasoning. Friedgut tells you, if you didn't have sharp threshold, then it means that you're very local, and you're a junta. And if you're a junta, then you can take this set of variables and use it to change the function a lot. So in particular, you're not pseudo-random. Okay, so this is the way sharp thresholds enter the picture. Yes, so this pseudo-randomness notion is really a central feature in the proof. Good. And yeah, so let me now state the regularity lemma, and then we'll take a break. And informally, this lemma says that any family F can be partitioned into a union of pseudo-random families with some junk, which is hopefully small.
And this union is finite, has a...
Yeah, so I'm going to say it more formally now. So this union, not only is it finite, it is over only constantly many families. So let's say it in a bit more detail. So it says the following. So pick your pseudo-randomness parameters R and epsilon. Then there exists a J and such that the following holds. If you give me a family F, then I can find a set of variables T, which is not too large, such that if I restrict these variables, I get a pseudo-random family with high probability. That is, if I take a random sample according to restriction, and I look at the restricted family, then the probability that it is not pseudo-random is small. Okay. Yeah, so this is a very useful lemma. So we're going to use it now for extremal combinatorics, but there are numerous applications of this lemma outside it. So there are also some applications in probability testing and constructing pseudo-random generators. So if you want to remember only one thing, then from this talk, then this is really it. It's a really useful tool. The proof is not too hard. I'm not going to show you that. If you've ever seen the proof of any regularity lemma, then you can guess that you define some potential function, and then you show that as long as you're not sufficiently pseudo-random, you can increase this potential function further. And this is indeed the way it is proved. But we'll use it in a black box. Yeah, so let me maybe say a few more words before we take the break. So let me tell you the rough sketch of how we're going to use this lemma to find our junta. So I'm not really going to start the proof, but I am going to tell you how to find the junta. So suppose we have our intersecting family. And we know that it is at least delta in size. So we're going to pick some pseudo-randomness parameter R and epsilon. Don't worry about them too much. We'll choose them in the end. Probably will not choose them at all, but think of them as R as being large and as epsilon as being small, but both constant. So what we can do by the regularity lemma, we can find a set of coordinates t, which is not too large, such that the following holds. So I'm going to draw it in a picture. So let's write t to be I1 to ij. And I want to draw the tree of restrictions. So I have some node, and then I split according to whether I1, I choose it to be inside or not. Then I split according to I2. And so on and so forth, until I get to the leaves. Okay, so for example, this leaf stands for the restriction of t going to t, and this one stands for t going to the empty set. Okay, so here is what our junta is going to be. The variables of the junta are going to be this t. And then the actual junta will be, so we look at all of the leaves, and we're going to clean it up. So if a leaf is not pseudo-random, we'll throw it away. Secondly, if a leaf has average close to 0, we'll also throw it away. So we'll throw something away if not pseudo-random. Or small. then we'll be left with only a few leaves, and this will be a junta. So let's write it. So G is going to be all of the subset of n, such that if I look at the junta variables T, then this is a leaf that is pseudo-random, and it's not too small in measure. Okay, so this will be our junta. So after the break, I'm going to tell you why this junta nearly contains the original family F. This will be very easy. And then I'm going to tell you why this junta is intersecting. Yeah, so I think that we'll take a 10-minute break now and then come back. Yeah, so let's continue. Yeah, so before I told you the rough sketch of how we are going to get the junta. So let me say that again, because I want to stress like one point. So we look at this. So we applied the regularity lemma on our family. We got this tree of restrictions, and let's ignore some details. We got it on all of the leaves. Our restrict family is pseudo-random. Okay, let's say that this is what we got, and we want to prove that if we take the family G that considers all the good leaves, all the leaves that are pseudo-random and sizable, then we want to say that this family is intersecting, and we want to say that it is roughly containing F. So let's answer the first question. So this is true because if a measure of junk so the contribution from the non-pseudo-random part is small. This is by the regularity lemma. And secondly, we also removed things that are of small measures themselves. So overall, they are also small. So when I say small, I mean things that do not satisfy this inequality is also small. So this is why you get that F is almost containing G. I guess that up to 2 epsilon, but never mind that. So that's sort of the easy part. So why is G intersecting? So this is the question that we want to answer now. So let's look at these trees, at this tree, and we look at two leaves that are considered inside G. Let's say we have this tree, H1, and this leaf, H2. So we want to show that the paths leading to H2 and to H1 intersect. So what we want to do is
draw.
Yes.
Perhaps you should say, I mean, it's sort of trivial, but you should say that H1 itself, like any leaf itself, contains only intersecting elements. That all sets inside the leaf are intersecting.
No, so that's not true, right? Because we may fixed I2 to be inside.
Yeah, I know, I understand. I think it's worthwhile saying before you, yeah.
And
or is it too trivial? you want to say that every pair of sets in this union is intersecting. Some pairs are inside the leaf, and some pairs are in two different leaves.
Yes, it's a good point. So yeah, because F itself is intersecting, any element you take from any two leaves or the same leaf, they're intersecting because they're elements of F. So yeah. So what did I want to say? So I wanted to say the following point. So we want to prove that the junta is intersecting, but recall that the junta, it only depends on the path from the root to the leaf. Once you get to the leaf, anything can happen with the rest of the variables. So the only way these two families, H1 and H2, are going to intersect in the junta is if the paths leading up to them are already intersecting. So we want to prove that paths leading to any two good leaves, H1 and H2, are intersecting. Okay, so this is sort of equivalent. If you want to prove that our junta is intersecting, this is really what we want to prove. Okay, so we'll do that by the way of contradiction. Assume that this is not true. Then we have our H1 and H2. These are two good leaves, and the paths to them are not intersecting. So if the paths are not intersecting, but the family F is intersecting, then this means that whenever you take an element from H1, which you recall already discards some variables. It only involves non-junta variables. And you take an element from H2, then they intersect. Okay, so this property, by the way, is called cross-intersecting. So that says that we have two families, and whenever you take one element from one and one element from the other, they intersect in non-empty. Good. So note that the only thing that we know about H1 and H2 are that the junta chose them. Meaning we know that H1 and H2 are both sizable, meaning measure at least epsilon, and pseudo-random. And we want to prove that they are, and finally we got that they cross-intersect. So the lemma that we want to prove is that this is not true. If you have two sizable families that are pseudo-random, then they are not intersecting. Meaning they contain two disjoint sets. Okay, so this is really the heart of the matter. This is really the most kind of difficult part of the proof. And we'll not do it in this generality. We'll prove something a little weaker, but it still carries most of the idea. So we'll prove weaker. We'll prove a weaker statement, which is the case that H1 and H2 are the same. So lemma. So suppose H is pseudo-random with parameters R and epsilon that should be chosen carefully, and the measure is not too small. Then H contains two joint sets. So this is what we prove, and this is the missing piece.
This is a stability theorem, right?
Sorry?
This in itself is a stability theorem.
Yeah, but quite a weak one, because it doesn't tell you really too much about the structure of H. It only tells you something very modest.
Yeah, but the fact that it is not intersecting is structure.
Yes. So there are several proofs of this lemma depending on what you know. So if you know some heavy tools like the invariance principle, then you can prove it like in 2 lines, but we are not going to use that. We're only going to use the basic sharp threshold result that we've seen. So it requires a bit more effort, but still it's a very nice idea. So proof. So assume H is intersecting. So we're doing it by the way of contradiction. Okay. And yeah. So here's something very amusing. We're not going to really use the fact that H is intersecting, but rather a much weaker property that follows from it. Then the half measure of H is more stuff. Okay. And if you recall, this is the most basic claim we've seen about intersecting families, because otherwise they contain some set and its complement. And this is all that we're going to use about the fact that H is intersecting. Good. And yeah, so now we want to use the derivative. So let's try to say something about derivatives. And probably this is a good point to say, which I forgot, that all of this business, we're going to prove it only when P naught, the P that we're looking at, is bounded away from half. So I should have said that. That's like something that we need for the proof that I'm going to show you to work. So let's say that for concreteness that P naught is like a quarter. but you need a little bit of distance from half. That's all you need. And this one P naught is this P. Okay. So let's look at this expression. Let's look at the difference between the measure of H on half and P naught. Divided by the difference between half and P naught. So this is kind of a proxy for the derivative. And if you use this assumption, or actually you don't even need that, you only need to use the fact that P naught is bounded away from half, then you get this is at most some constant, say 4. Okay. But this proxy for derivative, we know that it is the derivative of this mapping at some point. So by Lagrange, we know that this is equal to the derivative of this measure with respect to P at some point Q for some Q between P naught and half. Okay. So this is the way sharp thresholds enter the picture. So what do we know? We know that the derivative at this point Q is at most 4, most some constant. What that means by Friedgut's theorem, we know that our family H on mu Q is a junta. So let's do it a bit informally. So I don't want to get into this closeness to junta. So let's just say that it is a junta itself. So it depends on a set of variables. And the only thing that I'll care about the size of T is that it will be less than R. Our pseudo-random
Maybe T is the wrong name because we had T in the, but.
Yeah.
Yes.
Yeah. Yeah. So this R is the pseudo-randomness parameter. This is the only way it will enter the picture, and this is how you actually use it. Good. So let's look at our family H. We know that it is S junta. And now we want to say something which is trivial, but it's important. So let's look at the mu Q measure of H. So if you remember, we're only talking about monotone families, and in particular, H is monotone. So when you increase Q to half, you only increase the measure. So the mu Q measure of H is at most the mu half measure of H, which is at most half by the property, by the basic property. So what that amounts to saying is, what I'm trying to say here is that the family H on mu Q is not everything. It has a measure that is bounded away from 1. So in particular, there is a setting for the junta variable as A, such that when you fix the junta variables to A, you get measure 0. Okay, so I'm only using here the fact that this is less than 1. Okay, is that clear? That's really the crucial point. Because now the proof is done in the following line. So let's look again what we've seen. We got this set of variables S. It has a small size. Its size at most R. And we argued that you can fix it to some specific values such that you get measure 0. So again, now using monotonicity, when you look at P naught, which is smaller than Q, you also get measure 0. Now this is already a contradiction to the pseudo-randomness. Okay, so let me say it again. So we started by arguing that there is this point Q on which the derivative of mu p of A with respect to P is at most 4, some constant. We concluded that the family H is a junta at this specific Q. We said that is not the entire family of subsets, and therefore we can fix it to some specific value such that it is nothing. And this is a contradiction to the pseudo-randomness of H. Okay, so this is the entire proof of the lemma. Yeah, so we sort of finished this lemma, and by a very similar way, you can also do the first lemma, but I don't want to get into that. Good. Yeah, so that's all I wanted to say about the Dinur-Friedgut theorem.
Can you just state it again, the Dinur-Friedgut theorem, so we remember what it all proves?
Yeah, very good. Yeah, so this is the Dinur-Friedgut theorem. So we have a family of subsets, capital F, and we have some parameter P that is bounded away from half. I should have said that. And we know that the family is intersecting and sizable. Then the only way it can be is that if F is nearly contained in an intersecting junta. So this is the theorem that we proved. So because we're on this slide again, we've actually defined the pseudo-randomness notion. We've shown the regularity lemma, and we finally proved this lemma saying that pseudo-random families are not intersecting. And I hope that it was at least somewhat clear, but I guess that it takes a while getting used to, that once you combine all of these ingredients, you actually get a theorem. Yeah. So this was a lot of words. And so now we're going to get a little less technical. So what we've just seen is what is called now the junta method. So this is really was introduced by Dino and Friedgut in their paper. And this is the basic method of taking some problem in extremal combinatorics and trying to say that if you have some family that has some property, in this case intersecting, then you can approximate it by a junta. And then if you want to study some more things, studying it on juntas is probably much easier. And so recently this method show a lot of activity. So there are lots of papers by, so let me get the references right. So there is a very nice paper by Keller and Lifshitz. There is a paper by Friedgut and Reger. There is another paper by Ellis, Keller and Lifshitz. And there are a lot more papers. And these papers really took this method to maybe new heights and showed how you can use more notions of pseudo-randomness and very interesting set of tools to prove lots of interesting results. But what I want to say is that this method tends to work whenever you have the following two properties. So first of all, you want your extremal examples to be juntas. Otherwise, there is no to look for, so you need to do something else. And secondly, and this is a bit more annoying, is that this set of techniques usually works very well when your bias parameter P is bounded away from 0 and 1. So this is not entirely true. So for example, for this Erdos-Corrado stuff, you could have done also any P, but for other problems, you really need P to be bounded away from 0 and 1. And this is really for two reasons. So the first reason is that if you look at P that is small, let's say, the regularity lemmas that you can prove are much weaker. So that's one thing. And secondly, P that is small, the analytical machinery that we have is much weaker. So we know some results, some of them are very nice, but we don't know anything as satisfying as a Friedgut's result. So that's certainly some challenge. So in the rest of the talk, which I guess is 20 minutes, I'm going to tell you a little bit about new, or maybe I should say some older sharp threshold results and new sharp threshold results in this regime. And then I'm going to tell you one or two things you can do with these new results in extremal combinatorics. Good. So let's talk about that. So we're going to switch now topic completely back to the beginning. So we have our function f. And again, we assume it is monotone. And we look at the mu p measure, but this time, in contrast to what we've done so far, we think of p as small. Let's say p is equal to 1 over root n. And so recall that what we want to do is we want to distinguish between these two behaviors. We want to distinguish between a sharp threshold and a coarse one. And the reason I'm drawing this picture again is that note that now the question is close to 0. Okay. And when we say sharp threshold in this regime, what we mean is that you have an increase from 1 minus epsilon times p to 1 plus epsilon times p. So the increase has to be narrow as a function of p. So when p is small, it's a stronger requirement. Okay. So what turns out to be the quantity that you need to study when you care about this sort of increases is you need to, again, to look at the derivative, but actually you need to multiply it by p. So let's adopt this p naught notation. So this is what distinguishes between these two behaviors. So then the question, suppose I tell you that this quantity is small. What can you tell me about f? Okay, it's really the same question as in the previous case, but in the previous case, p was bounded from 0, so it didn't matter if we multiplied by p. It was the same question, but now it matters. And actually, we do not know the answer to this question. We have some conjecture, but we don't know to prove it. So let's get the obvious guess of the table. So is f, does it have to be close to a junta? So if you are, you may expect this thing to be true if you've seen what we've done earlier, but this is not the case. You have other examples. So you can show that any constant with DNF formula satisfies the property star. So I'm going to call this property star. And because we look at small bias parameter, this DNF may depend on many, many variables. Okay. So this is a counterexample to your obvious suspicion that the function must be a junta. And actually, we conjecture is roughly all that you can do. So this is a conjecture by Friedgut. Essentially, it says that if f satisfies star, then it must be close to DNF. I want to state this conjecture is only for monotone functions. Yes, so this would be a very, very nice result if it is proved. But as I've said, we don't know how to prove it. But some results are known. So let me tell you a little bit of what is known. The first result is by Friedgut. So Friedgut was interested in studying some graph properties and the k-sat function, which turn out to be really related to this small P regime and to this sharp threshold question. And for him, he had some symmetries to his function. So he proved that if you have enough symmetries, then this is indeed true. So he proved that the conjecture is true. If F has sufficiently many symmetries. So I'm intentionally being vague here, so it's not clear exactly what he needs, but for example, it works for graph properties. Okay, so so in his paper he proved this result, and then he conjectured that symmetries are not needed, but we don't know how to show that. So what about the general case? So here there are a few partial results. One of them is due to Bourgain.
Dora, sorry, can you show again the property star?
Yes, so property star, you should think about it as the function has a cost threshold, but when appropriately normalized to take the fact that P is small into account.
Okay, cool.
Yeah, so this is how you should think about it, but formally you multiply by P. Yeah, so there are some partial results about the general problem. One of them is due to Bourgain, another one is due to Khatami. So I'm going to tell you what is the result of Bourgain, and then I'm going to tell you what it lacks and what we improve. So here's Bourgain's theorem. So suppose F is monotone. It has a constant measure, and this property star holds. Then what Bourgain wants to show is that in this case, you have some local structure. And what he shows is that then there exists a small set of variables let's say smaller than k. I'm cheating a little bit, but never mind. Such that if you fix these variables to 1, again, we're using this notion of restrictions that we've defined earlier, then this set of variables really affects your function in the sense that it increases the average of f from what it used to be plus some e to the minus k squared factor. Okay. I guess I should also require that it is not of too high measure. So again, this theorem really aligns with the first statement that I told you in this talk. If you have a coarse threshold, then you get local structure. Local here refers to the fact that the set T is small. So this is the result of program, but as I already hinted, there are 2 points that you can ask about. So issues. So the first issue is that, well, is it tight? Is this e to the k squared result tight? And this is mostly for interest of whether a result is tight or not. I don't think that it has any like major significance. But the second point, which is of more significance, is that can you prove the result when your function has a small measure? So recall that we had this requirement that our measure will be at least some constant. And this is very annoying because sometimes when you want to use it, for example, in extremal combinatorics, the functions that you are dealing with actually have small average, like the dictators, for example. So you really want to be able to say something about this case.
Do?
Yeah.
Does it make sense in order to prove towards proving property star is somehow relax the factor p you multiply the derivative with to, we know it when you don't use p there, then we know it. It's like, and maybe if you put the square root p, or I mean, is it known that the Friedgut conjecture, the analog of it, if we put square root p there or some other function of p that's bigger than p?
No, so I don't think so. So if you remove this p altogether, then it's fine.
Yeah.
But other than that, no.
It makes sense to you to try?
Hmm?
It makes sense to you to try approaching it this way?
So this multiplication by p, it makes a lot of sense when you look at the notion of total influence. Because this p times derivative is exactly the average degree.
Yeah.
So from this point of view, this is really the correct thing to look at. But you can look at some other, so it's less natural for sure to look at a different function of p. But I don't think that it's normal.
Okay.
Good. Yeah, so these are the two issues that we have with Bourgain theorem, but luckily we can get rid of both of these issues. So this is a theorem. So finally I'm saying something new. So this is a theorem of Kivash, Lifshitz, Long, and myself. So we give a tight version of Bourgain that also holds for small measure. So the formulation is really the same. You have a monotone F. You don't assume anything about the average. You only assume, but you do need to insert the measure somewhat into the picture. And the way you do that is you multiply the right-hand side by the variance of F. then in this case, again, you can show that there exists a small t such that when you fix this t to be 1, then you increase the measure significantly. And here significantly is exponential in k. Good. So this is related to, again, a stability problem of the so-called edge isoperimetric inequality, if you know what it is, but I don't want to say too much about it. And we managed to use it to prove some things in extremal combinatorics. And I want to only tell you about one of them because we're kind of short on time. So Andre will correct me if I'm wrong, but this is like one of Andre's favorite problems. And this is the so-called Erdős matching conjecture. And this is a generalization of the Erdős theorem in a different way. So in the usual Erdős we looked at our family F, and we did not allow, we forbid F to contain two disjoint sets and we ask how large can it be. So you can consider like many variants of this problem when you have more than two sets, when you have a different domain. There are many variants. And the variant that we care about here is the following. So this is the Erdős matching conjecture, or the Erdős matching problem. So we have S, and we have our F, and we forbid F to contain a matching of size S, meaning S pairwise disjoint sets. What can it be? And for this question, it makes more sense to look at uniform families, meaning to look at families of subsets of n of size k. And then we can ask how large can it be. And so the story here is not so simple, but one thing is clear. So the question only makes sense when n is more than k times s, because otherwise you don't have enough elements in your universe to contain s disjoint sets. And there are two regimes for this problem. There is one regime where n is like bounded away from k times s, and when n is roughly same as k times s. And in each one of these regimes, we expect the extremal example to be different, but today I'll focus on this regime. Yeah, so how do you generate a family F such that any S, such that it does not contain such configuration? How do you generate such family? Well, here is one natural way to do that. You look at the family F of all the subsets, that contain at least one of the first S-1 elements. Okay. And then if you look at any S sets, by pigeonhole, at least two of them will contain the same element from S-1. So it will contain no such configuration. And the conjecture is that this is the best. At least when n is sufficiently larger than k times s. Yeah, so I ran out of pages and probably out of time. So I'm not sure what to do.
How can you run out of pages?
I don't know, I'm clicking and they don't work. Yeah, so anyway, I'll
You have to buy a new laptop.
Yeah, so
but perhaps you can finish what you wanted to say about this.
Yeah. Yeah, so this conjecture is still open, and the best result is due to Frankel and Andre. They proved it as long as n is at least 5/3 times k times s. They use really different techniques. They don't use any sharp thresholds or any of this fancy stuff. But what we managed to do is, so we can prove this theorem too, when n is at least some large constant times ks, which is a weaker result than the Frankel-Krupowski. But actually, we can also get stability. We get approximation by junta, and we can get that if you have a family that is does not contain this configuration and is large, then it must be close to the extremal family. And actually, we get a more general result for not only for matchings, but for what is called expanded hypergraphs. Yeah. But I don't have enough time to tell you about any of that, so I'll just end it here. Thank you.
Okay, thank you very much. It was a wonderful talk on a blackboard. Very impressive. Whiteboard, sorry. Anyone want to ask any questions?
Yeah, I mean, maybe I should give a very small comment that there were some stability results for Erdős Corrado before, but of different kind of spirit, like Hilton-Milner type results that would only look at the distance from the junta, well, from the dictatorship to the family, and then that would be quite efficient in some regimes also. And we also had a similar thing for Erdős matching conjecture, but it doesn't really go as far as Dünner and Friedgut, because you only kind of look at the distance from one junta or dictatorship and not see junta.
Any more questions or comments?
I have a question. Yeah, I don't even know how interesting it is, but is there an analog of Dünner Friedgut for Gaussian spaces?
So what do you mean by intersection in Gaussian spaces?
Well, I mean that yeah, you have a stability result of a similar nature. I mean, one can probably formulate it. The question is whether.
Yeah, so the tricky thing is to say what is intersecting, because if
you might try
say
to
that,
say you know, like a family of vectors whose inner product is at least something. But yeah, somehow I don't know anything about this.
You don't know. You didn't prove anything.
Yeah. So
actually, I was yeah, it has some geometric applications, and I would be really interested, even in the case -101 of -101 vector. Somehow it's natural to look at scalar products there, but it's really unclear the Junto situation in particular, because I think what is very important for this setting and this, you have this notion of monotone families. You can close the families upwards. There is a very natural kind of order, you know, that 1 is better than 0. But even if you go to -101 vectors, there is no such order, kind of.
And so this is a very good point. So in the second thing that I didn't tell you about that we can do with this sharp threshold result is in a regime where there is no natural ordering like you have on the p-bias cube. And then it doesn't really make sense what sharp thresholds even are. But you can come up with different notions for that. So there is a very specific idea that I can tell you about, maybe offline, Andre, that sometimes is useful there.